Hello, I'm Archit, and this is the final project presentation. So our topic which we chose for presentation is graph data processing analytics using MongoDB, and we are group 6. I am Archit Sangal, and two other of my friends are Aditya and Gagan, who are there in this team. So the problem statement which we chose was basically to provide the users who are using this tool which we have developed. I would call it a tool or a library to quickly load the graphs, which includes generating random graphs or some standard graphs, which could be an online available graphs, network graphs, etc., and process them, analyze them. Basically, we have developed a whole aggregation pipeline using MongoDB, using the aggregation pipeline feature. And, also, we have kept in mind the demands of the users, like say filtering, grouping, and like most of the graph-based operations. I would be discussing them in a minute. And our overall objective of this presentation was to develop a reusable set of components. So so our project is basically divided into multiple scripts, and I would be calling each script as a component, and all of the components are basically taking some graphs as an input or some other input variables and giving us a graph or another component which could be used further. So this basically makes it very usable, because suppose if you are taking a graph as an input and giving a graph as an output, so if this component is, say, if the components are arranged in like component 1, component 2, component 3, in that case we can just say that, yeah, we can switch between the components. Suppose the component 1 was initially the first one, it could be interchanged. So we will be discussing on this in my demo. So this was basically the motivation for the project was we were giving 5 categories, and out of those 5 categories we thought we want to try something new, something out of the box. So we thought we can choose graph data processing and analytics category, and yeah, we wanted to try something new. Also, this project seeks to address the issue which I've just described earlier, because there is no such library which we found online when we researched, when we were submitting the proposal. We didn't find any of such libraries online for MongoDB. We wanted to address this issue, and we thought we can develop it on our own. And yeah, so the large graph processing and analytics would be very difficult, especially if the graphs are stored in a database. So it's basic. So this project caters to that problem and solves this problem, which is difficult and time consuming. So the approach we have taken here is that first we get our data set. Data set is basically the graph. So like we found many graphs online, but the formats were different. So we assumed that if the formats are same and we convert it into either an adjacency list or an edge list, then we can process on that. And for this purpose, to make to continue with the generality, as mentioned in the guidelines, we have used a synthetic data set. We can make we have scripts which can generate, and I would be and our team would be submitting those scripts as well, which basically generates the required code, required graphs. After making those graphs, we can have the components. So we develop the components. Components are the scripts on which run on the graphs, take graph as an input, and produce a new graph which could be further used by another component. So in a way, however you want to take it, you can just replace the component one after the other, or according to your needs. And you can use one component as many times as you want, and you can just interchange the sequence also. And as MongoDB uses JavaScript, so you can use other features of JavaScript as well, like if conditions, loops, etc. But obviously, then there would be some kind of efficiency issues, because they would not be using aggregation pipelines. So it depends on the user needs, and we have given our user an option or what to choose from, and the scripts are basically reusable. So it all depends on user, how the user wants to use it. For analytics, we are using a library which is JSNet. So what we do is that after we have made changes to the graph, or we have found out different aspects of the graph, we finally save the new graph in a new, like basically in a file, in a .js file, and then we export that file. And we use that file in JS Network X. We will be discussing we will be discussing this later. So yeah, so for the making of the graph and parsing it, now Gagan will take over and he will explain the next part.
Hello, I'm Gagan Agarwal, a member of Group 6. I'll be explaining how we're generating a synthetic data set of graphs. Basically, for our project, we needed both undirected and directed graphs, and we wanted graphs to have a specific number of nodes that we want for different algorithms, so that we can test them properly. We couldn't find any small graphs data set online, so we decided to go ahead with generating our own graphs. As you can see here, with using a library called JS Network X, this library basically provides functionality called binomial graph. This binomial graph basically allows us to generate a random graph with j nodes, where an edge is generated between each node pair with a probability of 0.6, and we're specifying the number of nodes to be generated as well. So a file graph5.json will have 5 nodes. As you can see here, we're converting the generated graph to an edge list format. We're also assigning random weights, because inherently the functionality does not provide weights, and we need weights for our shortest path algorithms in the analytics. Also, as you can see, we're exporting the graph, the edge list, to a JSON format, so that we can import this using into our MongoDB collection. We're generating both directed graphs and undirected graphs. Basically, a directed graph has an edge in only one direction, from U to V, whereas an undirected graph has edges in both directions, U to V and V to U. And we're exporting both as JSON format files. As you can see here, a directed graph has these edges 0 to 2, 0 to 3, 1, 3 to 3, whereas an undirected graph has it in both directions, so 0 to 2 and 2 to 0, and 0 to 3 and 3 to 0, and so on. We can also generate complete graphs using this library, where basically each pair of nodes has an edge between them. This generates graphs like this, where there's an edge between each pair of nodes, like 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3. Once these JSON files are created, we use our Mongo import Mongo import command line to import these graphs.json files into a collection. Basically, we are specifying the DB name here, the collection name, and the file. And since the output is in a JSON array format, we specify the JSON array format here. And this imports the graph into a collection. That's how we're generating the synthetic data set of graphs.
I would like to start off with the README file. So all of the instructions you will be mentioning are properly described here in the README file. The README file is quite verbose and contains all the instructions. And there should be no problem in running the file according to us, because we have written it quite in detail. So first, like after the graph has been exported to a file, we will import it into our MongoDB. So yeah. So I have two terminals here. So one terminal is this terminal, and like the normal terminal, and the second terminal is the Mongo SH. So I just log into Mongo SH, and yeah, this terminal, in this command what we are trying to do here is that we are importing Mongo. So what this command will do is that it will import into the database graphs a collection called as graph 10. Graph 10 being denoted as that there are 10 vertices in the graph from the file undirected graph10.json. This could be generated as described by Gagan, and yeah, we just import it. And you can see that the graph is being imported like this, and similarly we can import other graphs. This is just for an example, and we can check this here in the test. So first of all, I would be using the other using the database graphs, and now I would be showing you the graph. So the name of the graph was graph 10, and now you would be seeing what is inside that collection. So you can see that it's a graph with u being the starting vertex, ending vertex, and the weight on it, and you can see the complete graph here. So you can type IT for seeing the rest of the graph. This is quite a big graph, so you may need to have multiple instances. So it has a lot of edges. Okay, so this is inside Mongo SH, and this is where we would be running our scripts. Okay, so I would be explaining the aggregation pipeline. So we have imported our graph, and we would be basically contracting our edge, one of the edge, and yeah, here is the code for it. Suppose you have an edge which we are contracting to find the minor, and that edge is being given us as an input. So what happens is that we have something as so we have this script which we will be running, and before running any script, on what collection or graph it would be running on, that depends on the input. So we have taken into consideration that we are assuming that our database may have multiple graphs. Each collection is a graph, and in this case we are taking the graph to be in form of an edge list. So if it is in form of an edge list, in that case we can take minor of a graph by passing the variables to the script first. So this is the variables. So suppose our graph name is our collection name in which the graph is stored is graph 10, and suppose the intermediate collection name, this is basically collection which in which our algorithm can store the intermediate result for better processing, for better I would say for better algorithms. So algorithm needs some kind of a place to store the intermediate results. So I'm just mentioning, say, intermediate, and then I have I'm finding minor. So say our output is stored at minor 10. Explain a bit what is how do we take a minor of a graph in this algorithm. So what we do here is that in our script, which is basically taking input as where this graph is stored, where will we store this graph, these kind of intermediate graphs, and where will we store the final graph. So what we will do is that in minor, what we do is that we delete some edge. Suppose this edge needs to be contracted. So if there is an edge, you need to contract it. So you contract this edge to get a new. So basically, for contracting this edge, you delete this edge, and whatever. Suppose you're contracting this one. So suppose you're contracting this edge, the graph becomes like this, and these vertices need to be the same now. So what happens is that basically this edge will come to this vertex, and so what happens is that we already have a triangle, and as this gets merged, this vertex gets merged into this. So this graph will now result into something like this. So now we have another edge. We basically have two edges here. So this is a multi-edge graph. So we also have a property. We also have a script for removing multi-edges. So the user can use after using the this merge, taking the minor. The user can also use the merge script, removing the multiple edges. So what that script could do is that it will remove these edges and add the weights to the newly made edge. So that is how the reusability is being used. Coming back to the aggregation part. So, so this is the input where our graph would be stored. This is the location where our intermediate graphs will be stored, and this is the final location at which the graph, at which the final graph will be stored. So what will happen is that this edge V will be deleted, and all of the edges which are incident on V will then be incident on U. So yeah. So what I can do here is that I will show you the graph first. So this is the graph 10 which we created earlier. Suppose it has this edge 0, 5, and the weight is 10. So what I can do is just make this change to be 0, 5, and 10. And now it's very simple because this is in this minor. So what I will do is I will go to my readme file, find the script for the finding the minor. So this is the script, this one. So you can see here the graph here, and I can just paste the script. Yeah. So so what happens is that first we take the name of the database. So the name of the database is graphs. This has a variable graphs. Then we take those variables, and then we run the script. So the script has been completed. So now if we see in our graph, we are showing it at minor 10. So what I can do is that I can use db.miner10.find, and it will basically show me all the graphs. So this will show me the resultant graph. So we are removing this vertex 5 and merging the edges. So wherever you see a 5 here, so these kind of edges won't be there, and instead what will happen is that they will get merged, and there would be a new edge which will be added from so this edge 6 to 5 will become 6 to 0. So yeah, this is the graph, and you will see that there is no h5 neither on this side. So neither there are edges which are getting out of 5, or neither there are edges which are coming to 5. So you can look into this. So I'm running, these are all the edges. You have to, this is a big graph, so I have to run IT a lot. So yeah, so we're at the end of the graph. So you can see that there is no 5. So that means that our vertex 5 was deleted, and if you see, the 0 will appear many more times than usual. So yeah, this weight is here, so ignore that. This is the weight, not the vertex. So these are the vertices. So if you see that there are a lot of zeros, because we also have taken okay, so for some reason there is this UV this side, and after that there is UV this side, and the weights are here. So anyway, yeah, so what we can do here is that you can see that there are no 5s here. You can check the correctness of the algorithm. We have checked it from our side, and we are pretty sure that we are pretty confident that it is correct. So yeah, this is how we use it. And then what we can do is that once we have done our operations, so if I go to one of the other graphs, suppose if I'm trying to find a weakly connected component, so we also have components of a graph. So we can find the components of a graph. This is a pretty long script, and I've already described it in the document. So what this script does is that it will find the individual components of a graph. So suppose you're finding weakly connected component of a graph, what we can do is that we can connect to the server, then we can change the directed graph to an undirected graph, and then we can find the components of a graph. So if you notice that this is also a pipeline, right? So this is also a pipeline, and now if someone uses a script like here, you can see that we can use this kind of a script for weakly connected components. This is actually a pipeline, but this pipeline is also being used as a component. So this is the power of our design, that even if like a pipeline could also act like a component. So once you have made a pipeline, it is very usable, and it could be reused in many of the other projects which you might be developing. So yeah, user gets this kind, and it's very easy for the user. So what the user just need to do is that define a set of variables like what we have done here. So the user basically defines a set of variables here, and then run the script. So this could be stored in a SH file, or however the person wants to store it. It could be a JSON file, a Python file, any file. And then after we have declared the variables, you can just directly run it. So yeah, that is it, I guess, the script part of it. Now this is the script, and I would be explaining the script. So I would be also taking reference from this. So first of all, we take the database name, connect to that database, and store that reference in this variable. Once we have that variable, we take the input collection name. This is also a variable, and we also take the edge which we want to contract. So once we have taken that, what we do is that we copy that script. So we copy that graph. Once you have copied that graph, and these are the variables which are used for copying. So you can see the reusability being used, and the like the independence of the components being used there. So we just define the variables and use the script. So we copy the script and we use the intermediate thing. So what happens? Like, so when you're using this, that's first part of the like whatever intermediate collection name you're giving. You cannot have a collection or a graph being stored which starts with that intermediate collection name. So once you have defined these two variables, you can copy the graph, that intermediate graph. So what we are doing is that we are making a copy of this graph. And in the copy of the graph, we are deleting the two edges. So it may be a directed or undirected graph. So we are assuming it to be an undirected graph. So what we are doing here is that we are deleting that edge. Like in this step, we are deleting this edge, and then we are using this aggregation. So in this aggregation pipeline, what we do is that we match. Suppose we match that if either u or v. So we are finding those edges in which either u or v are there, and if those kind of edges are there, such kind of documents. Each edge is like is stored in form of a document. So if such a edge or a document is there, which contains, in our case, let's say 5 here, so it will separate it out, and once it has been separated out, what we will do is that we will check that if u so is it an outgoing edge? So it checks that u parameter is equal to 5 or v parameter is equal to 5, and then we replace that u parameter or v parameter here with the other. So if it is so if we are deleting say 5. So if there is an edge, say from say 1 to 5, so now the new edge will become 0 to 1. So what we are saying that if we are deleting this vertex, like in this vertex, so what will happen is that this edge will basically change to something of this sort. So if this is A and this is B, so A will remain the same, but the vertex which we are deleting, this B vertex, will become for this edge from A to B will become say A to C if this is C. So that is what we are trying to do here. And then we are storing it into our intermediate collection. So this was intermediate underscore copy. So we are storing this time in it at intermediate collection name. So once we have copied this, so what we have right now is that we have a graph in which these edges which are incident to this is deleted. So we have this kind of a triangle which is stored at this intermediate underscore copy location, and then the newly constructed edges which we constructed here, we add it to this graph. So that is what we are doing here using another script which is okay, so yeah, so we are basically a union of the graphs here. So we can actually use a script here. Okay, so this is the same. I must not coded it there, but yeah, we can use a script union here. So that would be nothing much, just the way we define the variables here. We can use similar kind of thing here. For now, I'm leaving it. You can check that in then just notice this part of the code and merge. So you just have to update the variables here, and this same script is here. So instead of writing this script, you can just directly use something of this sort, which looks like a bit of abstraction, and user don't have to go through that. Then after this, so in between these two steps, what I'm doing here is that I'm again defining some variables and again using this script. So this script basically deletes the variable v. So this is a subgraph induce subgraph. So induce subgraphs, what it does is that it deletes this vertex and this edge with it. So it will just delete this vertex and the edges incident on this. So what we'll have is we will have a triangle like this and something of this sort. So just for repeating it, first we copy it, then after copying it, we find out the vertices, which are the vertices which you have to switch, like which are the vertices which were A to B becomes A to C, and then what we will do is that we delete, in this graph, we delete this vertex V, so it becomes a triangle, and then after it becomes a triangle, we add the vertices, we add the edges A to C, and we get a graph, and what we finally do is we store it in the original collection. So yeah, that was it. Now once we have, suppose if I want to export that newly made graph, so what we can do is that we can use Mongo export, so yeah, something like this. So yeah, we can use this kind of a Mongo export. So this will export the graph which we have made to the file. So you can see that it has been exported, and yeah, we can just find that file here in the output section, and we have our file. So this file can be later imported to analyze it visually, which my friend Gagan again will be explaining. So yeah, that's how we do it. So as I mentioned that so like we have multiple components which we have designed. There are total 17 of them. So I cannot go through each and every one, but yeah, we have seen that weakly connected component are based on like some scripts. So weakly connected component is based on undirected to undirected, and if you want to copy the graph, you can use copy graph, and then you can find the components of a graph. So these are the hierarchies. First you have to define these, and then this, and if you're using this, then this whole thing will act as a pipeline, and this whole pipeline will act as a component. So suppose if you are making a topological minor of a graph, you will have to use minor, which in turn uses induce subgraph, and merging or taking union of graphs. So this is also a complete pipeline, and if you are using topological minor, so this whole part gets abstracted to a component, and this pipeline will also be used like a, how should I put it, like a component. So it's very usable, it's very user friendly, and the demo part or the analysis part of it also has a visual part to it, so that also is quite user friendly. So for the analysis part, we will be using these two libraries, so my friend Gagan will be taking over.
Now talking about the data analytics part, as you can see, we've written a script here that takes and import a JSON file of the graph, and we create a graph using a JS advocates library, and we can perform operations on this graph that we just created, such as finding the cliques, the number of cliques, the maximum size clique, and things like number of nodes, number of edges, as well as the shortest paths between all pairs of nodes. We've also created a user interface for this. Apart from just running this file directly, we can also execute this in the browser. So first, let's just check this out in the terminal. As you can see, it outputs the graph first of all, the edges that are present in the graph that can be seen here as well. It's the same graph, and then it outputs all the cliques that are present in the graph, the number of cliques, which is 3, and the maximum size of the clique, which is also 3. And it also tells us the shortest path from node 0 to node 4 is through this path. We can check this to visualize this. We've created a d3.js file, HTML file, where we can basically take this graph as an input and output it on the browser. So we've written an HTML and JavaScript file for this. So we can start an HTTP server basically and open this file in the browser. So as you can see here, this is the output on the browser. As you can see on the left here, we have our graph, which we can move around. So as you can see, we saw that the number of nodes are 5, number of edges, as you can see, are 6. And the shortest path from node 0 to node 4, as you can see, is in fact through 0 to 4 and not 0, 3, 4, because the 0, 3, 4 path adds up to 13 in weights, and 0 to 4 adds up to 12, and hence it has shown the shortest path. It also outputted the number of cliques and the size of the maximal clique. These are only these are some of the operations that we applied. The user, according to their needs, can apply any of the analytical operations they want on the graph and visualize them in the browser.
So yeah, our scripts perform quite good, we would say, because our scripts perform exceptionally well on small graphs, obviously, and also on graphs of size 100 and 1000. So if you see that these time to get the graph, the importing of the graph is pretty less, and copying the graph from one database, from one collection to another collection, is also pretty good. So there are total 17 functions, 17 components or scripts which we have written. I've listed some of those here, and yeah, so you can see the statistics. It performs really good, and the time increases as the size of the graph, basically the vertices or the edges increases, and finding the component of a graph is quite involved too, and finding the weakly connected component, as this script uses component of a graph, is obviously more expensive. So yeah, so our conclusion is that MongoDB is indeed capable of handling graphs, and the graphs could be, the number of vertices in the graphs could be as high as 1000 vertices, and MongoDB was able to handle it quite well. The scripts which we wrote were quite user friendly, had quite a good user friendly interface, and they were quite reusable. The evaluation results were also quite good. So that is our conclusion. So we learned a lot doing this project, and we found that using join operations could be really expensive. So one of our aggregation pipelines was taking too much time to run. So when we tried to find out that why it was taking so much time for running on a graph which was of size, I would say a little close to 1000 that time which we were considering, it was taking a lot of time, and what we were doing was we were using a join operation. Because of that, it was taking so much time, and we basically found out that, as many times discussed in the class and in the presentations, that join operations could be quite expensive. So we had to change the logic of that algorithm. So we were using weakly connected component at that time. So we changed the logic, and then it worked pretty well. It was connected components of the graph, and then it was working fine. So we were able to get our results in 4 seconds, even for 1,000 vertices graph. We also found some of the stages which MongoDB provides for the aggregation pipeline, like graph lookup, which performs DFS or BFS on our graphs. It was basically DFS, but yeah, you can modify it to get BFS also, I think. But we used DFS, and it was quite non-intuitive. It was basically not intuitive at all that how to use it. But eventually, when we was working on it, we got a hang of it, and yeah, we were able to figure out how to use it. And yeah, just one of the thing was that this was completely an out of the box idea, and we were working on graphs. It was a very nice experience, to be honest. And yeah, thank you.